These are just a couple examples of how you would use the concept of voltage and potential energy that's there when you have two charges, say like charges, that are squeezed close together. That would make a lot of potential energy because they'd want to blow back apart. So what's happening in this case is we've got, it's +2 nanocoulomb charge that's held in place. Okay, so this thing can't move. And then what's happened over here is somebody has chucked 100 gram or 0.1 kilo positive charge toward this thing, and it happens to be moving this fast. And so to think about what's kind of going to happen with this thing, right, is these are two positive charges. So they, in general, will not want to be together. There's going to be a repulsive force between them all the time. So this thing happens to be moving in at the moment, but there's a repulsive force on it. So what's going to happen with this thing is it's going to have to come in, and then but as it gets closer, the repulsive force gets bigger and bigger and bigger. So it's going to slow down, and then it's going to have to turn around and then just get repelled away. And then off it's going to go. And so the force between these things is always repulsive. So this thing just will want to get thrown away. So something that's being asked here is, well, how close will this get before it turns around? And so what we can do, the type of physics we can use to figure this out, is actually energy, conservation of energy, which I like to kind of express it as like an E before equals E after. So I'm going to say E before equals E after. Before is going to be when we're at right now at the 3 meter mark, and then the after, if we're looking for the turnaround, is going to be, well, at the turnaround. So if you look at the type of energy that you have before, this thing is going to have some kinetic energy. So it's got Ke. I'm just going to put with a 3 underneath at 3 meters. It's going to have some potential energy at 3 meters, electrical potential energy. And then that's going to be equal to, now at the turnaround point, it's only going to have potential energy because it will have stopped moving. So Pe at the turn. Right? And so, right, all the joules that it has here, which are now expressed as potential and kinetic, as this thing gains potential, it loses kinetic, and then at the turnaround, it's going to have all this potential energy before it gets thrown away. So this is how we can figure this out. So at 3 meters, it's got 1/2 mv squared of kinetic energy. So let's just put that in. So we've got 1/2 m, which is 0.1, and then the v squared is 4, and then we got to square it, or v is 4, and then we got to square it. So that's your kinetic energy. The potential energy is going to be QV, all right? So plus, and then our charge, so we're going to use potential energy is Q times V, right? The Q, or the charge, is 0.5 coulombs. Right? And then we have to calculate the voltage at this point that's created by this charge. So that's KQ over R. So Q times, now we got to do KQ over R. Well, the K is 9 times 10 to the 9th. Q is 2 nanocoulombs. And this is why I made it nano, just to make the math easy. 2 times 10 to minus 9. So that will cancel that. KQ, and then divided by R, divided by the 3 meters, right? So that's the total energy that it's got before, and then we need to get the potential energy at the turn. So again, QV 0.5 now times the voltage created by this charge, KQ over R, 9 times 10 to the minus 9, 9 times 10 to the 9th, excuse me. 2 times 10 to the minus 9 divided by the R of the turn, the location where it turns around. And so it looks like the only unknown now is this, so that means we've solved it. And so now we can calculate this. I think this is simple enough where we can get most of the way without the calculator. So this is going to be 4 times 4 is 16, half of that 8 times 0.1, that's 0.8, plus this should be 9 times 10 to the 9th. So those cancel. 9 times 2, 18 over 3 makes 6. Half of that is 3. So 0.8 plus 3 on this side equals 0.5 times 18, which is 9, divided by the radius of the turn. Or the location where the turn happens. So to get the location where the turn happens, it looks like we just have to do 9 over 3.8. So the location where the turn happens is 9 divided by 3.8. 9 divided by 3.8 is 2.37, let's round, 2.37 meters. So it turns out that is where it's going to turn around. So at 2.37 meters. Right? Then the next thing it asks for is the maximum speed of this object. All right? Now with the maximum speed, where's that going to happen, right? Well, this thing is coming in at 4 meters per second. It's going to slow down. All the energy will become the potential energy at this point, and then it's going to turn around, fly back. Now by the time it gets back to here, it's going to need to have exactly that much speed, but in the opposite direction, because the total energy needs to stay constant. Well, as it continues to move away, it's going to always be pushed by that charge, right? So what we want is for the total energy to be constant, and since it's always getting pushed and pushed and pushed, the maximum speed is going to happen when it's super far away, because it's going to approach a maximum speed. So the maximum speed is basically going to be happen out at r equals infinity, okay, like way out there. And so what we want to do is say, okay, well, all the energy that this thing has then, by the time it gets out there, that is all going to become basically kinetic energy, right? You gain potential energy as you come in this way. You're going to go out to having 0 potential energy when you're out there. And so what all we need to do is compare do E before equals E after. So let's just do that part down here. E before equals E after. What I'm going to do for before is I'm going to take, well, here's before, and we know that it has 3.8 total joules of energy. And then our energy after is going to mean like at infinity. So it's going to have 1/2 mv squared of kinetic, 1/2 of 0.1 times v squared, and then plus qv. But you notice v out at infinity, when r equals infinity, that's going to be 0. So that would be the PE. That's the KE. Right? So you notice that the only term we have left is velocity. So we just have to go 3.8 times 2, divide by 0.1, take the square root, and we can get the speed. And it sure as heck better come out to be bigger than 4. So let's check this. So we're going to go 3.8 times 2, divide by 0.1. That'll be v squared, and then we'll take the square root of that guy and get 8.72 meters per second. Right, so it's going to approach that speed as it flies away. Starts at 4, slow down, no speed, build the speed back up to 4, and then fly away and continue to gain and gain and gain speed forever, approaching that number. So that is how you use voltage. Just use this like any other type of energy when you're doing E before is E after. If you have charges that are separated or together, pressed together, they're going to have potential energy that you can figure out from QV.